Swayam Prabha. Digital India. Educated India.
So, in today's class, I will discuss about turbulence. So, first we will look at turbulence in single phase flows without any particles. To start with, I have put this famous quote from Heisenberg, who was a German scientist. So, he says that if God is asked why relativity and why turbulence, he would have an answer to the first question, but not for the later. So, no doubt, turbulence remains one of the greatest unsolved problem in classical mechanics. So, in spite of studying turbulence over centuries, still we lack a complete theoretical framework to predict and to describe it. The inherently nonlinear, multiscale and chaotic nature of turbulence makes it the only phenomenon in classical mechanics that has registered a full analytical solution. So, in short, turbulence is still not fully known. Okay. So, now why this is the case? So, let us see that. So, for that purpose, first we will have to look at some key characteristics of turbulent flow. So, see the turbulent flows as such is so vast and it includes so many different aspects that it is not possible to include everything in a one full course. So, here what we are going to do is I will only give a brief background on the theory of turbulence, such that it will be helpful later when we discuss about numerical techniques for turbulent flow and also importantly particle turbulence interaction. Okay, so that is, so I will only briefly present the essence of turbulence. So, what are the typical characteristics of turbulent flows? Usually, we assign unsteadiness to turbulence. We say that if a flow is unsteady, it is turbulent, which is not fully correct. Unsteadiness is in the flow is not a sufficient condition. It may be a necessary condition. And this is also closely related to the misconception around this equation. So, when we talk about turbulence, we immediately write this equation and say that, okay, now I can decompose the velocity of the fluid into mean and fluctuation. So, again, you can write this equation for a flow, that does not mean that the flow is turbulent. Okay. Why is this so? So, let us look at the flow behavior past a cylinder. So, here you have a laminar flow past a cylinder. The Reynolds number is about 100. Okay. So, here you can clearly see the vortex shedding. So, for this Reynolds number around 100 or so, we will see periodic shedding of vortices behind the cylinder. So, if you consider any point say here in the wake, and if you plot velocity, you can expect something like this. So, if I take the mean of this flow field, this will be my u mean, and this would represent the fluctuations. So, does this mean that the flow is turbulent here? The answer is no. This is not turbulent, even if we can have velocity fluctuations. Now, you consider this case where the Reynolds number is very high, okay, about 3 lakhs or so. So, in this case, if we repeat the same exercise, if we plot the velocity profile, we will see, let us say, something like this. We may see something like this. So, in this case also we can find mean and we can have fluctuations. So, should we call this as turbulence? You will say yes. But what is the difference? Only that the signal is different, but in both cases we can define mean, we can define fluctuation. So, why we call this as turbulent flow only? So, for that purpose, you can have a look at these figures, these photographs first. So, these are taken from various flows. Say for example, in a sea, this is the behavior of a smoke stream generating from let us say an incense stick. This is how coffee and milk mixes. Here you see the clouds. This is a jet. Now, what do you see here is that here you have a presence of a range of length scales. Time scales we cannot gaze from here, but you can definitely see that it involves a range of length scales. What does that mean? That means, so if you look at this jet, you can see some large scale vortices. So these are the large scale vortices. You can also see some intermediate scale vortices as well as some small scale structures. See. So similarly here you have some large scale structures present, but imagine you can zoom in into the flow, you will see some fine scale features also in all of these cases. So there are large scale features, there are small scale features. So basically in turbulent flows, you have a spectrum of length scales, and that is why time scales also involved, in contrast to laminar flow. So if we go back to the previous case, so if you consider the power spectrum or Fourier spectrum of this flow field, maybe here you will get say one peak, or let us say two peak, or one or more discrete peaks. So this, let us say this is the spectrum corresponding to the energy of the flow. So in this case you have discrete length and time scales involved. For instance, here you can say, okay, the length scale would scale with the diameter of the cylinder, and the time scale would scale with the free stream velocity, so diameter divided by free stream velocity. Okay, but you have some discrete length and time scales present. In contrast, if we do the same thing in case of turbulent flow, you would see say something like this. The exact mathematical nature of this curve we will see later. But the point here is that here you have continuous evolution of the energy of the flow across different length scale of the flow. So let us say this represents the length scale of the flow. Actually in this case this is the inverse of length scale or length scale, it does not matter. So that is the main difference that we must remember in case of turbulent flows. So here we have range of EDs ranging from large scale to small scale. At least qualitatively this is evident. Actually and this takes us to the next characteristics of turbulent flow, which is known as energy cascade in turbulence. And for that we need to look at Richardson's imagination on turbulence. So he could imagine nearly 100 years ago that this is the case, that there is no specific time and length scales involved in a turbulent flow. In fact, he gave a poetic picture of turbulence, and this is a famous poem, you can say. Big wheels have little wheels which feed on their velocity, and little wheels have lesser wheels and so on to viscosity. So you can, means I am unable to imagine how he could imagine at that point of time that it is not only that a turbulent flow consists of eddies of different sizes, but he could think that there are large scale wheels, what he said wheels, these are basically the vortex, the eddies. And then that gets smaller and smaller, and finally viscosity plays a role. Now this is very important and interesting how he could think about this only by looking at the turbulent flows. So here basically now we have, this brings us to the energy cascade theory in turbulence, which says that we have large scale eddies which receives energy. Basically energy comes from boundaries or external forcing, and the large scale eddies are influenced by geometry or the mean flow. So for example, if you have, let's say, a jet, then the large scale eddy would be influenced by the radius of the jet. If you have a pipe flow, then the large scale eddies are influenced by the geometry of the flow, which means that the diameter of the pipe or height of the channel. If you have, let's say, flow past a cylinder, then it is the size of the cylinder. So these are the boundaries which influence the large scale eddies, and they get energy from mean flow, especially from the gradient in mean flow. For example, let's say here you have profile like this. So this velocity gradient which causes shear, that generates turbulence. At this moment you can think like that. So basically they are called energy containing eddies. The large scale eddies are called energy containing eddies. Then we have medium scale eddies which we call inertial scale eddies. So in this case the eddies interact non-linearly, breaking down into smaller eddies. So basically large eddies breaks down to smaller eddy. But the energy transfer is conservative. There is no dissipation of energy. So only that the energy, instead of being contained in few large eddies, now it breaks down to smaller eddies. So now the energy is contained in smaller eddies, and those eddies further break down, they produce even smaller eddies, but the energy remains similar. And this continues, but the question is how long this process can continue. This continues till we reach the smallest eddies. So smallest eddy means where we have viscous dissipation present. So by the time we reach such small length scale, the viscosity now dominates. So now viscosity does not allow simple cascading of the energy. Rather, the energy there is dissipated. It is lost. Lost to what? Lost to thermal energy. Okay. So at the smallest scale, the eddies lost their energy due to viscous dissipation. But it happens at that scale only. And that is known as Kolmogorov microscale, okay, where energy is dissipated to heat. So basically, so as of now, you may be thinking that, okay, all this sounds good, but is there a theoretical basis behind this, or it is only hypothetical? But this actually laid the foundation for Kolmogov's theory, which we will see soon. Then this energy cascading is closely related to a very important characteristics of turbulent flows, that is rapid rate of diffusion of momentum and heat in comparison to laminar flow. So why that happens? Because the large eddies essentially they move the fluid parcels long distances, while the small eddies homogenize at fine scale. So basically this momentum and heat transfer takes place now across the energy spectrum at different scales. So the large scale convective transport now takes place using the by the large eddies, while the small eddies they affect the molecular level mixing or the fine mixing. Okay. See here we have the small, we call them as small eddies, still they are larger than the mean free path of the molecules. Still we have the continuous assumption valid that you should keep in mind. We cannot go to that scale because the viscous effects are always dominant at a scale which is much higher than the mean free path. Okay. So because of this we have a combined effect of fast multi-scale mixing of what? Of momentum, heat and scalars. For example, let's say you take coffee, okay, you have concentrated coffee and you put, let's say, some milk in that. So if you gently stir it, it will take long time to mix, but once you stir vigorously, then mixing is quicker. Have you ever thought why that is happening? And when we say mixing, finally if you see the presence of the milk in the coffee, in, let's say, in some discrete form, or let's say layer of milk is present, till that time it is not mixed. When we say it is mixed, actually it has to be mixed at molecular level such that the color of the coffee changes. Okay, so that is affected by actually turbulence. Okay. So here it is important to see the distinction between molecular viscosity and eddy viscosity. So if you see in laminar flow, it is the molecular viscosity which is responsible for the momentum transfer. Okay. But in particular, it is not the dynamic viscosity, but it is the kinematic viscosity that plays a role here. That is why we call kinematic viscosity as momentum diffusivity. So higher the kinematic viscosity, higher is the possibility of momentum diffusion. So what is meant by momentum diffusion? So for example, if you have any flow and you bring, let's say, flat plate close to it, then the momentum diffusion mainly takes place in this direction because of the formation of the boundary layer. So you have immediately you have a velocity gradient, okay, and you have a shearing effect, and that is how the momentum diffuses. So the boundary layer thickness, which basically you can say that it basically represents the scale over which momentum is diffusing, that depends on the kinematic viscosity. Now, if we say that in turbulent flow mixing is improved, why is that? What causes that improvement? Do we have anything else apart from the viscosity? So here we have this, the kinematic viscosity, and here we can say that we have something called eddy viscosity, which is higher than the actual kinematic viscosity. Now eddy viscosity, what it is actually? So is there a physical quantity called eddy viscosity, like how we have kinematic viscosity? The answer is no. So, this is only a mathematical quantity which contains the velocity fluctuations also. So, eventually it is the velocity fluctuations which additionally facilitate additional momentum transfer in case of turbulent flows. So, basically you can say eddy viscosity is a kind of a model to demonstrate why momentum transfer happens in a faster way in turbulent flows. Next, the question is, why does turbulent flow behave differently from laminar flows? What is the reason? Is it because the governing equations are different from laminar flows? The answer is no. The governing equations are the same. So, if we consider an isothermal flow with no heat mass transfer, then what are the governing equations? The continuity equation and the Navier-Stokes equation. The equations remain same. So, if the equations remain same, how come its solution is different? Okay. So, the thing is, actually what happens in this case, even if the equations are same, the boundary and initial conditions, the changes in the boundary and initial conditions have a significant role, especially when we have high Reynolds number. Again, we can consider, say, the example of flow in a pipe. So, imagine one case where you have Reynolds number of 1000 and the other case you have Reynolds number of 10,000. Okay. So, if you see these two cases, and let us say if you are able to do an experiment and see the streamlines, let us say. So, in this case it will be very nicely visible, and that is what actually Reynolds did. If you remember Reynolds' experiment, so he released a dye at the center of the pipe and kept the flow laminar, so you could see the streamline properly. But as you go on increasing the Reynolds number, which means that as you go on increasing the velocity in the pipe, then you could see vigorous mixing. So, the question is why that happens. If you consider from a numerical solution point of view, you have same equations, you have same boundary conditions. Why the solution is different? You might have changed Reynolds number. Reynolds number means in this case again the diameter is constant, you are increasing the velocity. So, why the solution is different? That is what is interesting. Now, why that happens is because even if we assume that the boundary conditions are same, it is actually not, because here you have some roughness. It is impossible to create a perfectly smooth surface. Okay, so you have some roughness at the boundary. Not only that, in practical cases, the flow rate, when you say, let's say here you say I'm maintaining 1000 LPM of the flow. So, you have a rotameter where you set it 1000 LPM. So, you see that it stays at 1000 LPM only. However, there is always some uncertainty associated with the measurement. That is why we say, okay, it is actually 1000 LPM plus minus some value. Uncertainty or accuracy associated with this. Why do we have that? Because whatever device you are using to maintain the flow, let's say you are using a pump, it is impossible that it will send exactly 1000 LPM all the time. So, this itself may vary. if it is highly accurate, then the percentage change would reduce, but still it is impossible that you have this as 0. So these fluctuations at the boundary cause the difference even if we have the same set of equations. So yeah, so that's what I mentioned. Slight perturbation can cause flow fluctuations which eventually reaches a chaotic state. So what is meant by chaotic state? It is not same as random state. Sometimes we use this synonymously, but they are not same. When we say that something is chaotic is nature, this means that the governing equations are deterministic, but the details are unpredictable. You cannot predict the details, in this case the solutions. While something is random in practice means there is inherent randomness. For example, you roll a die. Now the outcome is always random. Whatever value you get, it is always 1/6. Okay, so that is called completely randomness. But what we have here is actually chaotic. But even if it is chaotic, random turbulence is random in practice. Why it is random in practice? Because it is impossible to know how the initial and boundary conditions vary. It is not possible for us to know, okay, or to have a model which will actually represent, okay, this is how the let's say the flow rate varies. At most you can say that, okay, it varies with certain probability, and I know the probability distribution which is Gaussian in nature. So the mean is 1000, but it can vary in some range. You can say this, but you cannot say that, okay, the next moment of time it will become 1000 will become 1000 plus 1. No, we cannot have control. Similarly, spatial variation also. At a particular location, maybe we can measure, but the next location, the roughness can vary actually. So this is the reason why the flow field appears random, and we have to treat this statistically. So what is meant by treating statistically? This means that whenever we describe turbulence, we don't use instantaneous parameters. For example, instantaneous velocity we don't use, while we do that in case of laminar flow. In case of turbulence, we use averages. For example, we calculate the mean, we calculate standard deviation, we calculate different correlations, spectra, PDFs. So we have to describe it as we do in case of a random phenomenon. Okay. Next, to to highlight this, what I am saying, the sensitivity to the governing equations, let's look at Lorentz system. Actually, Lorentz came up with this system of equations, which are basically 3 coupled nonlinear ordinary differential equations. And these are some constants. Now, what is interesting here is that, so you first start with some initial conditions. So these are basically initial value problems. So you start with some initial condition and you solve this, and you get, let's say, the value of x, which varies this way with respect to time. So this is time. Okay. Now you see, now I change this by this much amount. You see, so a very small change to one of the input parameters, and you see this. So you may say that, okay, well, they look similar, but Now let's calculate the difference, x minus x cap. So if we calculate, we get something like this. So what do you see here is that till time for about 35 seconds or so, the solution matches very well, very well. But after that you see large changes with this small change. So why this is happening? This is happening because of the nature of the equations and these constants that you have used. And this is only case of this is only a very simple case. Now imagine Navier-Stokes equation, which is highly nonlinear. Okay. So now what happens in case of Navier-Stokes equation? So if we look at that, so this is the Navier-Stokes equation for let's say for incompressible flow. Now if we write this in non-dimensional form by choosing appropriate scales, length scale, velocity scale, time scale, okay, then we get this where Reynolds number appears. You are aware of this. Now, what is the role of the Reynolds number? As long as the Reynolds number is low, viscosity dominates. And in that case, the nonlinear terms are weak compared to the viscous dissipation term. So the flow is smooth, laminar and predictable. There is no chaos. So you can argue that, okay, well, in this case, don't we have roughness? Don't we have fluctuations in the mass flow rate in the case of a pipe flow? You do. You have all this. But all those fluctuations are dampened out because of viscous effect. So that is the main difference. So these are present even in the case of laminar flow. So that is why you get a predictable solution. However, as Reynolds number increases, the nonlinear advection term overwhelms the viscosity. The small disturbances are amplified instead of damped because now the Reynolds number is high, which is the ratio of inertia to viscous force, which means that the inertial force is high. And this leads to instability, which causes the flow to transit to turbulence. And finally, the flow becomes chaotic, which is sensitive to the initial condition. And that is the reason why we have a broad band spectrum. So what we just discussed, that why we have a range of length and time scales in turbulent flows, this is the reason. Okay. And also, so here basically what happens is that the high Reynolds number unlocks the chaotic potential of the Navier-Stokes equation. So you can imagine that this equation has the potential to be chaotic, but this happens only after certain Reynolds number, and that is how we have the definition of critical Reynolds number. But interestingly, that critical Reynolds number itself depends on the geometry. Why? Why the critical number for pipe flow is 2000, while for flat plate it is 5 into 10 to the power of 5. 5 lakh. Why you think we have this difference? Why the Reynolds number, critical Reynolds number is so large in the other case? It is because of the presence of the additional boundary. So, I should not say additional boundary in case of a pipe flow, but the boundary effect is more significant in the case of a pipe flow. So, that is the reason why the critical Reynolds number is smaller there. Okay. Okay. So now we'll look at Kolmogorov's hypothesis. So now we have talked about the energy cascading mostly from a qualitative point of view. So Kolmogorov tried to bring in some quantitative aspects to Richardson's imagination. And basically this Kolmogorov's hypothesis lays this statistical foundation for turbulence. So this is a very important discovery in turbulent flows. Let's see what is the Kolmogorov's hypothesis. So first thing is that Kolmogorov assumed high Reynolds number. So before we talk about hypothesis of Kolmogorov, it is important here to know that this is valid only when the Reynolds number is high, so that turbulence has a clear scale separation. So what is meant by scale separation is that what I just mentioned, that we have different scales, large scales, intermediate scales, small scales. Okay. Without high Reynolds number, the arguments of universality and scaling, as we will see, everything would collapse. For example, we should not consider Reynolds number of, let's say, 3000, 4000, 5000 in case of pipe flow if we want to use Kolmogorov's hypothesis. In this case, it should be like 10,000 or more. Okay. So there are three main hypotheses. First one is local isotropy or small scale universality. What does this mean? That what he said is that at the smallest scales where viscosity dominates, we have the turbulent motions are statistically isotropic and homogeneous. And this is independent of the boundary conditions or flow geometry. Now this is interesting. So independent of what type of turbulent flow you consider, let it be a jet flow, let it be a flow past cylinder, pipe flow, flow over flat plate, independent of that, the behavior is similar at the small scales, and that is what is small scale universality. Now, what is statistically isotropic and homogeneous flow? So, in layman terms, let me first explain. So, in this case, we know that isotropy means there is no directional preference. So, what is independent of direction? You can think of like this. So, let's say you calculate the standard deviation of the velocity fluctuations. So, how do we calculate standard deviation? So, basically you subtract the mean and then you square it divided by total number of samples, square root of that. So, this is the standard deviation of velocity. Similarly, we can calculate u dash, v dash, w dash. So, are these instantaneous quantities, or so here I have used this u dash to represent the standard deviation. But if we write like this, here this represents the instantaneous value. So, we have to be careful. Otherwise, to avoid confusion here, let me just say that, okay, this is standard deviation, sigma u, sigma v, sigma w. Okay. So, we have three standard deviations, okay, defined in three different directions. But can we say that at any instant you have velocity fluctuations u dash, v dash, w dash? The answer is, or you have the velocity fluctuations sigma u, sigma v, sigma w. So, we can say that at any instant you have u dash, v dash, w dash. So, this represents the velocity fluctuations. Okay. But these three represent the standard deviations. So this is not defined at an instant. This is a statistical quantity. That is what we have to understand. These are defined, and when you have isotropy, when we say that the flow is isotropic, these three are same, but not this. This is what we have to understand. U dash, W dash, V dash are not same. At any instant they are not same. But if we calculate the statistics, if we calculate the standard deviation, then they are same. Okay. So that is why we have statistical isotropic flow. Not only that, it is homogeneous also. So now what does this mean? Now let's say here you have, at this point you have sigma u, sigma v, sigma w. At another point, let's say here somewhere, I calculate the same parameters but at a different location. So let's say this is x plus delta x, y plus delta y, z plus delta z. So it's a different location. So now if I say that the sigma u here is equal to sigma u here, if they are same, then this is homogeneous in x direction. Similarly, if I say that sigma v here is same as sigma v here, then it is homogeneous in y direction. Similarly, so homogeneous in z direction. It is possible that you have homogeneity only along one direction, not along two other direction. But if that is also, if everything is same, all values here and here, all are same, then we call that as isotropic as well as homogeneous. Okay. So here Kolmogorov argued that, or he hypothesized that at that small scale, if we calculate the velocity fluctuations, the velocity behavior is universal and it is homogeneous isotropic. Which means, so why it is universal? This means that they have, at that scale, they have forgotten what happens at the large scale. So whatever is the boundary condition does not matter. Whatever type of flow you consider does not matter. Okay. Second, the existence of inertial range. So he hypothesized that between large scale and small scale EDs, we have the inertial scale EDs. And this is called inertial subrange, where energy is transferred from scale to scale without any production or dissipation. What is production of turbulence? Mainly by the gradient in the mean flow, if you have a strong shear. That's what happens in case of large scale EDs. What is dissipation? Where the energy is dissipated to thermal energy. That happens in small scale. But in this range, nothing happens. No production, no dissipation. Only inertial effect matters. And neither large scale forcing nor the molecular viscosity influences the dynamics here. Now, all these have very important bearing on the energy transfer rate that he derived later. Then we have similarity hypothesis. So now he came up with a very simple logic to calculate the small scales or the smallest scales of turbulence. So what he argued that the statistical properties of turbulence, when we have small scales, only when we have small scales, it depends only on two parameters. One is kinematic viscosity or momentum diffusivity. The other one is dissipation rate, the rate at which turbulent kinetic energy is converted to thermal energy. And this is defined per unit mass. Now, you at this moment, you only need to look at the units. So here I have given units, I have given SI units, but you can generalize this. So here this is energy transfer rate. So the numerator here represents energy per unit mass. So kinetic energy per unit mass, and this is time. So its unit is meter per second cube. Okay. So now here we have this unit and here we have this unit. Now I ask you to come up with the unit of a time scale. So what would you do? If you just divide nu with the dissipation rate, you will get second square. So if you take square root of this, you get Kolmogorov time scale. That is the smallest time scale of the smallest ED. And similarly, by only considering the dimensions. So for example, now you take cube of nu and divide, you will get dimension of the length, and he could derive the expression for Kolmogorov length scale. What is the smallest scale? Similarly, velocity scale, and this is what you get. Okay, and this is purely based on dimensional arguments. But what is interesting is that now you calculate the Reynolds number and you see that it is 1. So what does this mean? This means that this is the smallest scale of turbulence where viscous forces dominate over inertia. So once you reach down to this scale, after that the viscous forces are now important. If we see the energy transfer at the inertial range, so here we bring in this parameter k, which represents the wave number. So this is basically called wave number. Which is nothing but this is the frequency. This is analogous to frequency in time domain. So if you calculate, see the frequency in time domain, you do this, right? What is t? T is the time period. So but now we do this in space. So if you consider the periodicity of the EDs, you have a large scale EDs. So this means that you have a larger spatial period. So you calculate now this parameter in for the space, then you get wave number. So this basically means that higher wave number means we have smaller EDs. So when this wave number will be higher? When the time period, or in this case the spatial period, is smaller. So that is why you have smaller EDs. So higher wave number means smaller EDs. So basically if you fix the wave number, then this means that you are considering a ED of particular size which scales with inverse of k. Okay. So this represents the ED at a particular scale. So now if you want to calculate the total kinetic energy, then you need to integrate the energy density function. Now you see what is E. This is something similar to the probability density function that we had considered. So this is basically the energy density function. So you have to integrate it over all EDs from 0 to infinity. So this is the total energy per unit mass. Okay. So now if we are in the inertial range, or if we are considering the EDs in the intermediate zone, then the energy transfer rate is governed by the interaction with nearby scales. So it depends only on the dissipation rate and the wave number. So you see that here now the kinematic viscosity is not coming into picture as in the case of smaller scale. So what Kolmogorov hypothesized is that if you are in the inertial range, viscosity has no role to play. Okay. So now considering that there is no net production or dissipation in this range, we can say that the energy is basically proportional to the dissipation rate and the wave number. So now we want to find what are these exponents. So what do? We just do dimensional matching. So just by matching dimensions, he could show that the energy can be expressed by this. And this is the famous minus 5/3 decay behavior. As we will see, if you look at the turbulence spectrum, this tells you that in this range, as the AD size increases, the energy would decrease. So basically, if you take log of this, and if you assume that this is a constant, and if you take log of this, you will get a decay rate, because here you have minus. So this is how he developed the hypothesis. Means Kolmogorov developed the hypothesis, and finally, why we call this as hypothesis? This is mainly because this is supported by dimensional analysis and physical reasoning, but these are not derived from first principles. Okay. For example, the laws of thermodynamics or Newton's law of motion. These can be tested empirically, but it cannot be proven mathematically from the equations. Then this hypothesis holds only at high Reynolds number. So this we have to always keep in mind, and it may fail in cases like turbulence with strong anisotropy, stratification, rotation, compressibility. So finally, Kolmogorov's hypothesis is a model of reality, but it's not the universal truth. Okay, so we'll continue this in the next class. Thank you.